Hello, today I would like to share our recent work on distributional value function factorization for multi-agent RL. This is my presentation outline. First, I'll talk about the background and motivation of our work. We focus on Q-learning in RL. If we have a single controllable agent, as in Super Mario Bros., then this is a single agent RL problem. Assume we want to jump to the top of the flag to achieve the highest score. Then we can model this problem as a market decision process with the optimization goal to achieve the highest reward. By Q-learning, we can learn a Q value for each state action pair. By acting greedily following the largest Q value, we can derive the optimal policy. In practice, the Q value is often approximated by deep neural networks, thus they are often prone to overfitting. In recent literature, distributional Q-learning is proposed to mitigate the overfitting issue. It models the full return distribution instead of the expected return. Such methods include C51 that models the probability mass function, an implicit quantile network that models the cumulative distribution function. If we extend to multiple cooperative agents, then this is fully cooperative multi-agent RL. The agents may behave differently depending on the current state. We can draw the reward matrix of these agents at each state. If we perform Q-learning for these agents individually, this results in a non-stationary learning problem. Therefore, in recent literature, value function factorization methods are proposed to learn a decomposition of the team reward into individual rewards. By such decomposition, we can perform Q-learning on the individual rewards to mitigate the non-stationary issue. Such value function factorization methods include VDN and Q-mix. Both of them depend on the individual global max condition. On one hand, distributional RL can mitigate the overfitting issue in Q-learning methods. On the other hand, the value function factorization methods are Q-learning methods that work well in multi-agent RL domain. It would be preferable if we can bring the benefits in distributional RL into value function factorization methods. However, they are not directly compatible to each other. Consequently, we propose the DFAC framework to bridge the gap between distributional RL methods and value function factorization methods. Then we dive into the proposed method, DFAC. DFAC includes three main theorems. The first theorem shows that by directly generalizing the factorization function to its distributional form is not enough to guarantee the satisfaction for IGM. In Theorem 2, we observe the fact that value function factorization methods only require the mean to be factorized accurately. As for the shape is only used for mitigating the overfitting issue. Therefore, we can approximate the mean by a complex factorization function and approximate the shape by a simple shape function. We show that the mean shape decomposition is guaranteed to satisfy IGM. The third theorem provides a practical implementation of the shape function and shows that quantile mixture is a valid approximation for the sum of random variables. This is the full network architecture of the DFAC framework. We can combine any existing value factorization algorithm with any existing distributional RL algorithm by such network. We further show that quantile mixtures has a better computational complexity when compared to other methods. Finally, we'll show the experiment results. We perform our experience on all super hard maps in the StarCraft multi-agent challenge. For each row, it is a super hard map, and for each column, it is an algorithm, where DDN and DMix are the DFAC variants. The upper portion is the win rate of the map, and the lower portion is the total reward. In this table, we can see that the DDN and DMix outperforms their baselines. The average win rate also demonstrates the benefits of DFAC. Thank you. If you would like to learn more about our work, you can refer to the QR code below for the full paper.